Welcome to Chapter 7, the second screencast for covalent bonds and molecular structure. We're going to continue with the idea proposed by Gilbert Newton Lewis, dealing with atoms being represented by the element symbol for the nucleus and the inner shell electrons, and dots to represent the valence electrons, and covalent bonding being a shared pair of electrons between two atoms. And we'll go back to the example of chlorine forming the molecule Cl2, and we'll recall that each chlorine atom has 7 valence electrons, and how chlorine ends up getting an octet around each of its two atoms is to have a shared pair of electrons between the two. So those two electrons are the bond, the covalent bond between these two atoms. This chlorine has 8 electrons around it, a filled octet. This chlorine also has 8 electrons around it, which is a filled octet. And the shared pair of electrons, which is the covalent bond, can also be represented by a line joining the two atoms. So a line represents a pair of electrons or a covalent bond. And the big idea here is that a shared pair of electrons is a bond, covalent bond. All right, enough of that. Now let's do some examples. So Lewis symbols can be used to represent the formation of molecules and molecular compounds, and we'll start with an example of the carbon-hydrogen compound, and we'll do the simplest one, which has one carbon atom, and a carbon atom has 4 valence electrons, and when it bonds with hydrogen, which has 1 valence electron, they can share electrons and make a covalent bond. Now that does not give carbon an octet, but if a second hydrogen bonds, and then a third, and then a fourth, we now have 2, 4, 6, 8 electrons around the carbon, and we have a bond to each of 4 different hydrogens, and this is the molecule methane, and this is the Lewis dot structure for that. If we do the compound with nitrogen and hydrogen, we'll do the simplest one, which is nitrogen, 1 atom. It has 5 valence electrons, and that means that 1, 2, 3 different hydrogen atoms can bond to a single nitrogen atom. That gives us 8 electrons around the nitrogen. Each hydrogen gets a pair of electrons around it, which is a filled valence shell for the nearest noble gas to hydrogen, which is helium, and everybody is happy, and this is the Lewis dot structure for ammonia. And maybe it's worth noting at this point, we didn't do this on the previous one, but we can also write this molecule as N bonded to H, bonded to H, bonded to a third H, and then if we do it in this form, we want to show that pair of electrons that's not bonded as well. All right, now let's do one with oxygen and hydrogen. And in this case, we have 1 oxygen with 6 valence electrons. That means it can bond to 2 hydrogens, which you probably could see coming. And this is going to be H2O, or water, with 8 electrons around the oxygen, 2 around the hydrogen, 2 around the other hydrogen, and if we draw the if we draw the structure for this showing the bond between oxygen and each hydrogen, we would draw the Lewis dot structure like this. So either of these forms is fine. It's probably more common to do the one showing the dot instead of dots for the bond, showing a line for the bond, but either one is okay. Now what happens if we have 2 oxygen atoms bonding together which is the diatomic molecule O2. Well, oxygen has 6 valence electrons. If it shares electrons with another oxygen atom and makes a covalent bond, you'll notice that we only have 7 electrons around this oxygen and only 7 around that. Now, there's only 14 valence electrons available for 2 oxygen atoms, so the only thing that can be done, and this is what nature does, is it takes one of these electrons from this oxygen and one of the electrons from this oxygen, and that gives us 2 more electrons in between the 2 atoms. There's no line there, just 2 dots. So here's a dot and here's a dot. And let's represent it like this. And what we have now is a double bond between these 2 oxygen atoms. And if we show this with the lines for bonds notation, we have O double bonded to O, and then we have several what are called lone pairs of electrons that are not involved in the bonding. And so this one bond here and a second bond there, that's a double bond between 2 oxygen atoms, and it's going to be stronger and shorter than a single bond. Now, the big idea with Lewis's electron dot notation is that atoms either gain and lose electrons or they share electrons, and now we're focusing on covalent bonding, which is sharing of electrons. And in either case, they try to achieve a stable electron arrangement like a noble gas. Yay! Okay. Now, can we use this idea for ions as well? And the answer is sure. And let's do an example of ammonium NH4+, and nitrogen has 5 valence electrons. Each hydrogen has 1 valence electron, but there's 4 hydrogens, and that gives us a total of 9 electrons, valence electrons for the NH4. But there's also a plus charge, and how something gets a plus charge is by losing electrons. So it loses 1 electron because it has a +1 charge, which means it really has only 8 electrons in its structure. So we have a nitrogen and 4 hydrogens around it. And if we put in 2 valence electrons for every place where there's a bond that's going to form, nitrogen to hydrogen here, there, and there, that uses up all of our valence electrons. It gives us bonds between nitrogen and each of the hydrogens, and then we put brackets and a positive sign to indicate that this is an ion. And then let's also write it as the other form where we do a bond between nitrogen and each of the hydrogens. And then we can indicate positive charge as before. For a nitrogen, 6 electrons for each oxygen times 3 is 18 electrons, which gives us a total of 23 valence electrons for the NO3 part. And then the negative sign means there's 1 more electron for a total of 24. And how we would draw this is N bonded to O, 3 different O's, 2 electrons to bond between nitrogen and each of the oxygens, and that gives us 6 electrons, and then we fill in 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and when we try to put in 23 and 24, if we put them here, that gives us octets around everything except for the top oxygen. If we put the electrons here, that gives us octets around everything except for the nitrogen. But if we put the electrons there, then we have 8 electrons around the oxygen, 8 electrons around the oxygen, same here, and 8 electrons around the nitrogen. The whole thing has a -1 charge, and how we would write this in our notation with lines representing bonds is N double bonds to O, single bonds to O, single bonds to O, and then we have 1, 2, 3 lone pairs on this oxygen, 1, 2, 3 lone pairs on that oxygen, only 2 lone pairs on this oxygen. The whole thing has a -1 charge. Now note that this is an example of what is called resonance, which is what happens when there's more than one way to draw a valid Lewis dot structure for a particular molecule, or in this case ion. And in the case of NO3-, the double bond could have been to this, what we'll call for now the top oxygen, but you could have equally drawn a double bond to the right oxygen or to the left oxygen. And it turns out that none of these are really the right description of the molecule or the ion. In this case, the actual structure is more like an average of these 3 possibilities, and that's what's called a resonance hybrid. And this is kind of a hard thing to wrap your head around sometimes, but it's something like the following, if we can make a kind of simplistic analogy. A donkey is something like a combination of a horse and a mule. So if you crossbreed a horse and a mule, you get a donkey, and the donkey is something like half horse and half mule. It's not alternating between horse and mule. It's an average of those two, and that's the same when we have a resonance hybrid molecule. In the real structure of NO3-, we don't have a single bond and two single bonds and a double bond. We actually have 3 bonds that are each about 1 1/3 of a bond. They're equal bond length. So what we have is 4 bonds distributed equally amongst 3 bond locations. And so we can represent it in this manner, where we show each of the possible resonance structures, so double bond here, or double bond there, or double bond there. And remember, it's not fluctuating between these. It's an average of them. It's not changing between a horse and mule. It's a donkey the whole time. And that's resonance. And another way to do this is to say, okay, we have really 1 1/3 bond here, 1 1/3 bond here, and 1 1/3 bond there. They're all the same, and we really have 1, 2, 3, 4 bonds distributed amongst 3 locations equally.